We're going to think about that more because we're going to measure it. You can actually measure the static friction coefficient. Very exciting thing to do. You could even measure yours. You could sit on a ramp and tilt it bigger. I've never done it myself. You would think I would have that on my CV somewhere. Let's see. Okay. So let's measure static friction coefficient, because that'll force us to do some free body diagrams and etc. I guess I could have just written µs. It's coefficient. Right? How do we measure it? So we're going to go back to our ramp situation here. So there's the ramp, like that. And let's say you can vary the angle. Okay. So let's assume that the ramp is at theta, but you can vary theta in principle. You could take the ramp, and this is what we're going to do, is we're just going to have this thing on here, and we're just going to say it's a tilt ramp, where I can sit here and go, oh, different thetas, different normal forces, different maximum friction forces, blah, blah, blah. So let's calculate some of those. Here we go. Okay, so here again, I'll just draw it real fast because we already drew it once. Here's the mass. I don't even draw vectors on that. We go straight to the free body diagram. mg, all right? The normal force, you know, has to be normal to that surface, N. And the friction, static friction, you know, has to be back. Fs, there it is. Let's see. So first, now let's think, what coordinate system do we want to work in? Do we want to work in x and y? No, because in x and y, you got to think about the components of this and the components of this, and mg is only in the y. You want to work in the coordinate system of the problem, right? So you want to work in, shoot, my m is in the way here. You want to work perpendicular to the surface and parallel to the surface. So you can think of it as I've tilted x and y. You can call it xy, x prime, y prime, whatever you want to call it. I like to actually use these symbols, parallel and perpendicular. Okay, so let's start perpendicular to ramp. The perpendicular direction, it's a Cartesian direction. You can write Newton's second law. Perpendicular, why not? Some of the forces in the perpendicular are equal to 0. It's equal to 0, not ma, because it can't possibly fall into the ramp, right? These are solid objects. Can't happen, all right? So we say it's equal to 0. And then we got to do this vector sum thing, right? So last time we went out of control and did every step and got the magnitude and the angle of each vector. Rather than just doing it intuitively, I am conflicted about what to do this time. Let's just go through each one and just see what we get here. Yeah, what the heck, let's do it. So for this vector, what is the component in this direction? It's the magnitude, n. Remember, if I write it without the vector hat, that just means the magnitude. Times the angle to get this component would be the sine of the angle from the x-axis, n times sine of 90. Okay, this is probably the last time we'll do it this explicit. Right? What is mg is straight down, mg. What angle is mg at? Oh, I thought I did this in detail. Oh, there it is. Let's see. Well, technically, with respect to this is 0, it's at, oh my God, 270 plus theta. Right? So I didn't write where the angle theta is. It's right here. Right? So we actually go all the way around 270 plus theta. So mg times the sine, 270 plus theta. Right? And then the last one is the Fs, right? So plus the magnitude of the static friction force times also the sine of 180 degrees equals 0. You're like, what is he doing? Let's go through the trig real quick. What's the sine of 90? Very good. Sine of 90 is 1. What is the sine of 270 plus theta? Oh, Google, sine of 3 pi over 2 plus x is negative cosine. It is. Minus mg cosine theta. Go check it yourself. What's the sine of 180? 0. That was exciting. Plus 0 equals 0. So what if I did this the intuitive way? I would say, what is the component of this in the direction perpendicular? It's n. Right? What is the direction of this in the direction perpendicular? Well, there's one component. There's the other component. Cosine is adjacent. It's mg cosine theta. Oh, crap, it's backwards. So we'll put a negative sign on it. Okay? So this is how we usually do it. But if this was like magic to you and you don't know where this came from, it's coming from here. Okay, so we're not going to keep doing that. It takes too long. I mean, it's okay for you to do it on homeworks and everything. But in the lecture, I'll just start doing them intuitively. But if you ever don't see where it came from, we can always go back and do it that way. Just raise your hand. Hey, I want to see that one in excruciating detail. Jump around and make us say the trig stuff too. Okay, so now let's do parallel. Okay, so what we learned here is the magnitude of n in terms of m and g and theta, right? So the normal force is just the component of the weight into the ramp. Right? And we did that before. We did that with normal force last time. But now we're going to do parallel to the ramp. Okay. And we're going to erase part of this really long equation because it's in the way. You saw it. You're with me on that one. Oh, sorry, I didn't have it on me. Oh, well, we can't go through all these. They're too long ago. We'll do the ones that say now. Can you go through how to find the angles? No. Never mind. Good. Wait. Why is f equals 0 perpendicular? This is the direction perpendicular to the ramp. The definition of the friction force is that it's parallel to the surface. So parallel is 90 degrees from perpendicular, so it has no component perpendicular. Right? Maybe that was the never mind. So you're doing good. Where did n sine theta equation come from? The one I just erased. We were doing the detailed conversion from polar to Cartesian. You'd have to go back to the first lecture to do it. So ask in office hours. I'll take you through it. Super careful. Okay. All right. Parallel to the ramp. Okay, let's see. Sum of the forces parallel equals what? Sum of the forces parallel equals 0 again. We're actually doing statics here. We're not letting it move. Right? Is this thing moving? No, not yet. So we're solving the static case. Sum of the forces parallel equals 0. So now we're going to do it the quick way. What's the component of the normal force down the ramp? 0. What's the component of mg sine theta down the ramp? Of mg down the ramp. It's mg sine theta. Right, this is mg sine theta. We call down positive. So mg sine theta. Sine theta. What's the component of the static friction force down the ramp? It's negative Fs. Okay, minus Fs equals 0. See, that could all be justified with detailed trig. And it will help some people and it will confuse others. Do we have a pledge problem soon? Good timing on that question. Excellent. Yes, we have a pledge problem soon. We don't know exactly when yet. We're still working on the details. A class is an organic living thing. We don't lay out the entire schedule on day one. We got complaints last year that they didn't have the date of every possible thing that could happen on day one. So a class is a living organism. Don't make me go on. Okay. So the friction force Fs. So what we're trying to solve here then is the friction force Fs. The static friction force is mg sine theta, right? That's the friction force holding that thing up. Now you say, wait a minute. I thought it was going to be, because you take so long to say things, I thought it was going to be mu times mg cosine theta, right? Because that's what this formula says. No, it doesn't. Is this an equal sign? No, no. The friction force will go from 0 to whatever you need to keep it from moving. So the friction force is not yet mu times mg cosine theta. Right now, it's only mg sine theta, right? It's getting there. It's getting higher and higher. Okay, so friction forces are not always equal to that. That's the limit. Remember, that is the limit. This is the alligator eating the big side. Is that how it goes? No, you didn't do that. Okay. You had to be from Florida, I think, to do that analogy. So what we're going to do now is we're going to show that we can actually measure mu. Okay? So what we're going to do is raise theta until it slides. Okay? Raise theta until it slides. All right? Let's see. What is the fancy mu on the left chalkboard? That is the coefficient of static friction. This is the Greek letter for m, I think. I don't know. I don't know. I didn't take any classics. I believe that is the Greek m. Someone correct me. The subscript is s for static. We use mu a lot in physics. Okay. Okay. So what we're going to do now is say, what if we increase theta? Right. So here I said the friction force isn't mu times mg cosine theta. It's mg sine theta. But eventually, think about it. As sine gets bigger, as theta gets bigger, sine grows and cosine shrinks. Right? It's good to have sine and cosine in your head. Right? Sine is 0 at 0, and it grows with theta. Cosine is 1 at 0, and it shrinks. So as I raise this, the friction force we need is getting bigger. The friction force available to us is getting smaller. Right? Friction force we need, mg sine theta, is growing. Friction force that we can have, mg cosine theta, mu times mg cosine theta, is shrinking. So eventually those two are going to cross, right? And what's going to happen? There, it slides. What angle is that? Somebody measure it. 30 degrees, thank you. So it slid at right around 30 degrees, right? So raise until it slides. Let's see. So let's see what happened, right? So Fs needed grew because it went as sine theta. This means goes as. It's not actually an alpha. I think it's a symbol physicists made up. Okay, it's not a Greek alpha. It means proportional to. I don't know the history of that symbol. I apologize. And let's see, Fs you needed grew. The Fs available shrank or shrunk? I'm going to say shrank. Goes as cosine theta. Shrank. Right? And eventually they cross. Okay? So eventually you reach the point where this saying that this equals 0 is no longer true. Right? So you lose it when mg sine theta equals mu s mg cosine theta. Right? So this is the condition where it'll start to slide, where this basically can no longer be 0. Right? This will be greater than 0. So if you plug in, you would get that this has to be true. I've run out of board, and we can't spend all the whole day on this. So what does this mean? Oh, mg. It means that sine theta over cosine theta equals mu static. Right? And sine over cosine is tangent theta. Right? So what this means is if you want to find the coefficient of static friction, it's just the inverse tangent. It's just the tangent of the angle. Is you measure the angle where it slides, and it's the tangent of that angle. Right? So here we go. It was sliding up, and it was about 30 degrees, and the tangent of 30 degrees is something. I forgot. I don't know. It's like a half or something. It's not a half. It's between 0 and 1. Right? It's 1 over the square root of 3, maybe? Possibly. I think it is. No, I don't know. Anyway, it's a number less than 1. And it wasn't even exactly 30. Whatever angle you get, you plug it in, and that tells you what the coefficient of static friction is. Okay? So you're like, yeah, maybe. Or you might be just full of crap. Right? So let me prove it to you. Let's get two objects, one that is very high friction and one that is very low friction. Okay? So very high friction is my phone because it's in one of these cases that helps you not drop it. Right? So it's rubbery. You don't want to drop your phone. And then this is the charger, which, as you know, is very slick because it's from Apple, right? So it's white and it's smooth. So which one do you think has a larger coefficient of static friction? The phone, right? So the charger has a smaller one, so it's going to go at a smaller angle than my phone, probably. There goes the charger, right? And then the phone, I mean, this is OtterBox level shit here, so I don't know if it's ever gonna go there. Oh, barely. It's vibrating too. Look at that. Right, so a much higher angle for the phone than the charger. So that helps your intuition and helps you believe in the demo. One first, and then the other. So if we wanted to, we could measure those angles and get mu s and turn it into an engineering project on them. Okay, so that's static friction.